Hello, welcome to ME 510, Economics and Policy of Engineered Energy Systems. This presentation is part two of our three-part module on coal, economics, policy, and markets. We've been talking about coal, the need for coal around the world, but let's now focus on the different types of coal. So on the left side of this graph, you can see that a visual representation of different forms of coal: peat, brown coal, subbituminous, and bituminous coal. When we classify coal, there are two things that we focus on. One is the carbon and heating value, and the second one is moisture content. When you look at the carbon and heating value, you can classify coals into two main categories: hard coal and low rank coal. Hard coal includes things like anthracite, which is the hardest of all coals, but it also includes bituminous coal, which is used for either thermal processes or metallurgical processes, such as steel manufacturing. On the left side, you have the low-rank coals, which include lignite and subbituminous. You can see what the purposes of these different types of coals or uses are around the world. And you can see the general percentages of their availability around the world. Now, why are there so many different types of coal? Well, it's because as coal matures, it goes from peat to anthracite. And this process is known as coalification. And this process changes both its physical and chemical properties. In terms of chemical properties, we can look at its ultimate and proximate analysis. This is just a representation of how much carbon, hydrogen, oxygen, nitrogen, and sulfur is in the coal, and some other energy relevant properties. One key thing to remember when we look at the proximate analysis on the left is that the distributions of fixed carbon and volatile matter have significant impact on how easy it is to combust that coal. Bituminous coal and subbituminous coal are among the most favored for coal boilers because they have enough volatile matter to make it easy to ignite. Moisture content is obviously important because the moisture content will rob energy from the process. Generally, you want as low moisture content as possible. Ash is an important factor because the ash can accumulate and cause fouling in boilers. And so generally, the lower the ash content, the better. And then you can see the distributions. Usually you want to focus on the carbon and hydrogen content. A high carbon content is usually preferred. Anthracite has the highest carbon content, but its hardness and other properties make it a little difficult to use in combustion applications. All these properties can be contribute to the net heating value of the fuel. And so again, you want as high heating value as possible, but in the case of anthracite, that comes at the cost of having a very difficult to ignite fuel. Now, if you look at the types of coals that are available globally, you can see that different countries have different quantities and proportions of hard coal and lignite. South Africa, for example, due to the World War II embargo, they developed a lot of coal conversion technology, and most of it had to be designed to process hard coal. Worldwide, about 37% of the coal is considered to be hard coal, and only about 4% is considered to be lignite. Now, when you combust coal, you're going to generate significant amounts of CO2, and one of the major challenges, engineering challenges for the future, is determining what to do with all that CO2. One of the key strategies that is being investigated or developed is carbon capture and sequestration, and the idea is that you capture the CO2 at the effluent from the power plant, and you immediately pipe it down to some reservoirs. And this figure shows some examples of reservoirs. Could be some coal beds, some oil or gas reservoirs that have been depleted, or deep saline aquifers. Now, if you look at where that carbon is going to come from, obviously a significant amount of CO2 is emitted by power generation plants, But you can also get CO2 from a number of sources, gas processing here being the second one, but you also have things like fertilizer production. Obviously, the lower proportion values here will be a lot harder to capture because capturing CO2 at a very small scale can be prohibitively expensive. I'm not going to read through this. The key takeaway from this slide, if you remember on my Kilby diagram, is that not all coal is, not all CO2 is easy to capture. And so um, knowing where the oil deposits are going to be can help you figure out what deposits might be available for CO2 capture in the future. Okay? And so there's a symbiosis here between CO2 capture and oil recovery. Some of these enhanced oil recovery techniques use CO2 as a way of pumping out excess oil from depleted wells. And so that's a potential market for captured CO2. Now, if you're thinking about what to study or work on for the future, CO2 capture is a promising market. And so you can see here some of the potential clients or sources of revenue for captured CO2. We just talked about using CO2 to help recover additional oil from depleted wells. But you can also use CO2 in other applications. Certainly beverages, we're all familiar with that, the food industry, but there are other applications to consider. And depending on the application, you can get a significant value out of that CO2. So anywhere from $9 to $26 per metric ton. Going back to what types of coals are available, if you look at different regions around the world, this slide simply shows in millions of tons the distributions of hard and brown coal that we saw in the figure, just to give you another idea of how much coal is available around the world and in different regions. The US is one of the countries with the largest reserves of coal, actually the country with the largest reserves of coal. In principle, the estimate is that at current use, we have over 300 years worth of coal that could provide electricity to the country. Obviously, some of that coal is easy to recover and some of it will be more expensive. But just in terms of energy value, the US could run on coal for 300 years and generate all its current electricity consumption. Followed by the US is Russia, China, and India, all countries that are heavily reliant on fossil fuels. Compared to other resources, coal has the highest reserve to production ratios. And again, this just speaks to the fact that we could use coal for a significant amount of time if we chose to focus on coal production. Oil and natural gas have a lower reserve to production ratio, but they're heavily used because they're cleaner, more convenient fuels. In terms of electricity prices, you can see that coal is generally the lowest electricity price option. If you have a supercritical coal plant, because of its high efficiency, you can reduce your electricity price to about $33 per megawatt hour. And you can see here how it compares to other types of energy, electricity production systems. Solar photovoltaics, well known to be very expensive, although those prices have been declining very rapidly in recent years. Wind certainly becoming a competitor, and depending on how you do the accounting and on some reports, wind and solar can start to compete with conventional coal power plants. So what can you do with coal? Now, we always focus on electricity, but actually coal can be converted into almost the same number of products as oil. You can use coal to produce substitute natural gas, synthetic natural gas. You can use it to produce ammonia, produce methanol. Dimethyl ether is the DME. Olefins, which are hydrocarbon building blocks for the oil chemical industry. So it's not just about electricity. You can use coal to produce a lot of other products. This concludes part 2. We will now move on to part 3.